Welcome to Tutorial 8, your first step into doing some work with linked lists, which will be very important for an upcoming assignment. So for today's work, I have set up an entire separated compile kind of program for you already that you can start with. So please go to the actual libraries directory under 1633 and copy everything from the Tutorial 8 directory. In there you will find a makefile to compile the entire program. You'll find tutorial8.cpp, which is the main file, and then all the linked list code and other helper functions is found in list.h and list.cpp. So you want to copy all the entire directory into tutorial 8 directory in your local home folder and follow along with the tutorial, and there will be a hand in with this that will require you to make sure that you filled in all code for the program. So not just what is the question for hand in, but you must also actually write the code that you'll follow along with me for the actual functions itself. So all of that work there. So you can see the makefile is like what you've seen before, is that it's got target set up, it's got the separate compilation for all of our files, and it has my general setup I've used for the lab to actually clean everything up. So you're clean, just checking for the code compiling, and the actual compiling and clearing the screen and running of the program, just since for these tutorials I recompile and run it a lot, so just to save myself time compiling everything. So it's the same makefile that you've seen before. So list.h is our header file, so it contains the structure and type def that's defined in the tutorial here, and then it has the actual prototypes for all of the actual methods that are in this tutorial here, and an example helper ones that you should have to include. The list.cpp that we'll go to in a little bit has the actual definition for most of these functions if they're done, and then some of them, like these last ones here, where they are skeleton kind of empty functions that we'll be filling in as we go through this tutorial. And the tut8.cpp just has calls, so including our lists, it has setting up and creating some different lists, writing them out to the actual screen. It has a call to doing a couple appends to show some variations of it and writing it out. And then it has finally a call to a reverse that's part of what you need to hand in, and then proper deallocation of all the lists at the bottom. So it's a full running program. You're not going to have to change anything in the main. You're just going to actually see as it's updated. Because right now, if you've got everything properly, you should be able to just hit make and it'll run, and you'll just get a similar output to what you see down here, which is just a whole bunch of gibbly goop because the right actual list is not done yet, and other things like the append and the reverse are not done yet. So you'll see as we finish these functions, this output is going to become a little bit more clear. So to start with, you are tasked with writing a write list method. So it's given the start of the actual linked list, and it must print out a formatted one of the opening and closing brackets separate outcome of all the actual data. So given whatever list, prints it out to the actual screen. So you're going to want to open up list.cpp now, and it has all of the actual demo functions in there. So now, even though the tutorial itself says only to actually create or work with the actual write list, I want you to be able to run this, and well, we can't write a list out if we haven't actually even built one yet. So I have created a method here for creating a list and for deleting a list. So this first create demo list, you give it a size, and it'll return you back a singly linked list of that number of nodes where the data matches up to the actual basically location where it is. So the first node will have data 1, the second node will have data 2, then 3, then 4, then 5. So you can see also an example of here how to start building and linking the data together. So creating the first node, so doing some dynamic allocation of node object, setting the data. I'm just being paranoid here, so I am setting head the next element to null to guarantee that this node is always linked to next until we add new nodes to it. And then I'm going through using a temporary actual pointer starting at the head to step forwards through everything. So we count and we keep creating the next node and then moving to it, setting the data, and making sure that our list ends with null. So coming back out of this actual create demo list is that it should have a blank list that's actually created. Now to visualize this quickly, I am just going to switch to OneNote and just draw it out. So let's just say that I had a call to that method and we were just giving it size 3 for right now. The idea is then you have the first pointers created and we're allocating a new node right here, and then we're putting the value 1 that's in it. Then after that, that links to a new one. So we're always having this one pointer called cur that's referencing to that in the very beginning of the actual code. So you can see that right here where we've made the new node right here, and then we've set cur equals to that head. After this, we're going through a count where it keeps stepping forwards and doing new things. So we go back to the code here. The idea is afterwards it's always going cur arrow next equals new. So we're following the arrow and we are accessing the node that it references to right here and then making a new node that it links to after that. We're then going cur equals cur dot next, so it moves over to the next one. So going up to the node, getting the next reference and moving to the one after. Right here. It then sets the data to 2 and then sets the next reference to actually being null, that there's nothing in there. And for these drawing right here, I like to use this symbol instead of an arrow for this one, is that symbol right there with the line is what I like to mark when I'm doing linked list work, just to visually draw it out being null. So after that with 3 there would still be another node, so we get the case of a new node being created from right here. We get the cur reference moving forwards. Right here we get the data value put in, and we have a marker here of null at the actual end to say that's the end of our list. And so at the end then this head reference is returned, which is that beginning link to the entire list that we have after this. Okay, switch back to here. So that's just the create node list, so I can make some new nodes as we go through it. Now, previous tutorials for allocating and deallocating is that we learned about the new command, and we know that when we allocate memory, at some point in time we're going to have to go through actually deallocating it. So after creating the create node method, I made a delete list method that you give it the starting of the actual list, and if there are nodes here, it goes through all of them, properly deleting it, and then it marks the actual list head with being null, and that's why we have a pass by reference. So you can see it here, or once again, I do what you need to commonly do with linked list is setting a temporary reference, or what I like to call a moving pointer reference, that is going to move through the list. So we start at the beginning of the list and we move until it's not null, setting it to here, controlling access to the data, move to the next node, and then delete the node that was right behind us. I don't want to go delete current and then access it, because we don't want to have any errors that could happen from deallocating memory and then trying to access memory that has been deallocated. That it could work sometimes or could crash other times, so it's better to keep a temporary reference to the node we want to delete, move to the next one that's after it, unlink it from the list just to be super safe, and then delete that previous one, and we've moved it here. So if we go back to our example here, if I was to go through deleting this, right now the idea is we set cur equals to the head. Pick a different pen color. Goes right here. We are then setting a temporary reference equal to what cur is. So right here. Then cur equals cur arrow next. So it moves to the next one after here. Then we're going temp null, like that. And then we are actually saying delete the memory. So the system has said that has been deallocated and that memory can be reused. And it keeps going through this same process. Again, temp equals that one, cur we can see even delete all of that. Cur equals the next one. Null, and then that's deleted. And all the way to the end, to the very last node, and cur goes off the actual end, and then we are setting the head reference to actually being null, so that there's nothing there. So that's the equivalent of the actual delete. So that's the delete list and everything else, and you can see in the main in the top, I create two lists in the very beginning of this, so I'm going to have to make sure that list 1, list 2, whatever else happens, everything gets deleted at the actual end. And so I do a lot of other work, and so just to be safe with all the other work that I'm doing here is I call my delete list on all 4 of those, just in case I've used them to create any list, to make sure at the end, so before I leave the program, that everything gets deallocated before we exit the actual program and when I'm done using it. So now we get to the actual write list method. So you have to write a list to step through here. Now, a lot of the work that we're going to be doing here, we have to start always at the beginning of the list when we're working with linked, singly linked lists. So we have that head reference, and then we're going to have to step through. So there's going to be a very lot of common code to actually do that, where we set up a node pointer using that type def we had before. And I like to call these current, but I make them equal to the actual start of the list. So that's the very first step. So I'm doing here, we'll add in code, I'm not doing any printing, I'm just getting something that's going to move through the entire list. So this is the very first step of it. Now I need to go through every node in the actual list, so I want to go so it steps through all the nodes and we stop when the reference is moved off the end of the list, which is marked by null. So we assume here, and so what this first while does here is that if this list is actually empty, so if head is null, there's no nodes right there, then we will not even go into the while loop and it'll skip over all of that. Now when we're in the while loop, if I don't do anything or change this code from right now, we will have an infinite loop because we're going while current is null. So if head isn't null, we're in here, we are sitting at the actual start of our list node, and then nothing changes that reference. So when we come back up, this will loop and continuously loop. So just like you would have learned in previous courses, if you're doing a counted loop, you need to increment some kind of variable and change that. We need to move our actual reference in the actual list. Now the equivalent of doing that move, and we're going to do at the bottom, is that we're going to do some of our work that we expect. What do we need to do with the node happens here. And then before we go to the next node, we always have a line at the bottom to move the reference, which is always going to kind of look like something like this. Is that you're saying cur. So remember that this is a pointer, and when we go cur arrow, we're accessing the structure, so we're dereferencing it, we're going into it and saying, okay, well, what do you point to? So this is really saying making our current reference then steps to the actual next reference right there, and it's going to step through. So this is going to be a general structure. If you need to go through every node in the list and not stop at every node, you can kind of have similar code. So setting reference to the beginning, stepping through until you step off the actual list, and then stepping through node one by one, since we only have a singly linked list to actually keep moving forwards. So if we go back to my drawing and go to a list to kind of visualize this sum, and oh great, I didn't even switch back from the entire window the entire time I was talking through that. I apologize, I can't go back and edit this video right now. So now that I realized I didn't control what screen I'm on, like my goof, so we'll go back here to the writing list. It's this code you're seeing here for this entire time, so my apologies. So you set a current reference to actual head. You have the while right here, so current does not equal null, so you don't move off the end of the list. And then you have cur equals cur arrow next for stepping forwards. So my apologies. So now if I go back to my actually drawing, and be careful switching through the actual screens, if I had a list, right this now of head, going to say just 2 nodes like this right now in a list. And so we'll say C is current. I'm making it equal to what head is. So that's not null, so it means it's going to go into the loop, and the next thing is it's going to go cur dot get next. So if I do get next, so the cur arrow, it means I'm following this, and then I am accessing what you see here. So this part of the actual list. So when I go cur.getNext, I'm moving up here, I'm accessing this part of it, and I'm saying, okay, well, what do you point to? And that points over to this one that's right there. So it means it's going to move to the actual next spot. Now it goes back to the top of the loop and it says, well, is current null? Well, no, it's not referencing a null node right here. And so then you say cur equals cur.getNext. So that moves at the next thing, but then it ends up setting cur to null, like this. And it means, okay, we've reached the end of the actual list and we are stopping. So that's a general structure that you have, and you'll see here I'm being careful, I'm switching back to the actual code, so we're good. Is this a general structure to move through? So this doesn't do writing a list, but it's one way to step through a list and start doing some of the work. And being careful here in the very beginning is that our list could be empty, so this first while cur does not equal empty for actual code, we'll stop it running if there's nothing else happening. So when it comes to the actual printing, we know that we first have to have an opening bracket before we go to print any data, and then when we're done printing any data, you have a closing bracket that we're going. We also then need to print out the actual data. So before we move the actual reference, like you see right here, then we can actually print out the data value. But we're not done yet. So this will print out everything. You can do it right now. We're going to have a few issues coming from right here. So if I even just go to our program right now, compile and run. Ooh. See, a few small errors is that I didn't use the proper null word keyword, so that should be in all capitals. And then missing one R right there. Okay, now when we're outputting it, we can see some of these lists. We're seeing some issues that it's not moving it down to the next line. There's no spaces in between the actual numbers, and there's no commas between any of it. So I can go fix at least the end part here now. We can see that they're all on individual separate lines. I now need to print a comma between each individual number. So that's easy enough. I can go just print a print number, print comma, should print out everything else. And we've got all of that, so it seems to be looking right for our lists that we have so far. We can validate the rest of the data in a second. But one issue is, in the required output, there should be no comma at the very end, but we have a comma here. So we have to detect again when we're reaching the end of the list, and if we're at the end, don't print a comma, only print as we're stepping through. Now, one way to actually do that is if we are at the last node and we're about to move off, what we can do is go if null. So we know at the end of the list is marked by actual null right here. So cur arrow next is equal to null. Then we can just, the next one is not null, right here, so not equal, so not equals. So if the next node we're going to move to is not null, print out a comma. If it is null, the comma will not be printed out because we are at the end of the actual list. There we go. We know we have a list, we have everything else printed out from right here. And so far we're okay for these first ones. So if we go to our main, My first list was just creating one of size 5 and size 4. So this first one should be 1, 2, 3, 4, 5, and list 2 should be 1, 2, 3, 4, and list 3 should just be blank, and list 4 should be blank. And we can see that we do have that here, right here, because we call here list 1 with those first printing coming out. So we can see that we have our proper printing happening now. Okay. Question 2 is now consider the actual function. So I'll go back to the list.cpp. And we're going to be moving on to the next function that's just below that, which is called append. Now this function right here, so you're supposed to consider this specification here where we're having append. It takes in 2 node pointers, supposed to be different heads, and is doing it passed by actual reference. So we can actually update the pointers that we're given. So this function appends the second list onto the end of the first. So head 2 pointer is set to null once the second list is appended. So basically everything that's in this list has to be added on to the end of this actual list here, and then at the end this one list here, the head reference has to be set to actually null. And so we don't do this by making copies or anything else, we are just updating the actual references. So why must each of these arguments be passed by actual reference? Is if we actually need to update them. Because we need to update what the start of these lists are. If they come in here, we'd have to return both, but we need to update the head and head 1 too. So this list has to be null in the end for that reference, and then this one has to be updated properly. So we need to actually be able to pass by reference to update the original head starting references. So we need to write the body of the function, and we also have to think of, can you think of one or more supporting functions that will simplify this algorithm? And there's a big hint, I've already got a header here for it, is getting the last node in the actual list. But we'll start with some cases for the actual append of what could be happening. And what we have to worry about is some special cases for how is everything in here actually broken down. Like what could be happening with the lists, and thinking about your test cases. And when this is coming in, one breakaway we can have is either the list has nodes or it doesn't have nodes. So what if head 1 doesn't have any nodes? So it would mean that this would be empty and this would be null. And we could have a case also that head 2 is actually null. So we need to worry about that. But the first thing is, okay, if head 1 right here is null, that first list is empty, well then to append everything onto this list, we don't add them onto the end or linking anything. We just have to make head 1 equal to the start of the actual second list. So we need to check for some of these things. So first we need to do a special case of just checking, okay, is the list we're appending onto, is it empty? So checking if it's null. If it's null, then I have to do one action of appending on. Otherwise, else, it means, okay, this list isn't empty here, and so I need to add all of these nodes from list 2 onto the ending of list 1. Now, no matter what happens after this, is by the end before we leave, then the actual second list has to be set to null. So what I'm going to presume is that I have done all the work properly, do the appending. It will be done in either the if or the else, and so by the time we leave, everything should be fine, and then we are just updating at the very last second, is the second list actually being null. So the very first one, this is a very easy one to do here. Is you're like, well, if this is empty, well then head 1 just has to equal head 2. And make sure that I have this updated here, so that's head 1. Then we just have to go head 1 equals head 2. We are just copying over the address, since head 2 points to the start of that list, and so now head 1 will point to what head 2 is, then head 2 is set to null, and since this is passed by reference, we have updated the list that was actually passed in, and we're done. We don't have to copy anything else. So let's quickly go and look at a diagram for that, so in the actual drawing. So if you're visualizing this, and trust me, I know most people don't want to do any of the visualizations, but it's very important to understand how the code is working. So we have in that case is assume that head 1 here is now null, so it's not pointing to actually anything. And then we have head 2, which is pointing to a list. Here. So what happens when we come in here, we can see, okay, head 1 is null, so we're just making it equal to head 2. So it points to the start of the list there. And then head 1 was head 2 is then set to null. And so when we come back from this, you can see that the head 1 list now has everything else appended on the actual end, and we only need to have the reference to the very beginning. Let's go back to the code and keep working on it. So next we've dealt with where, well, head 1 actually has no nodes, and we need to deal with that because there's nothing to actually link at the end. It's null. So now we have to deal with what if head 1 actually has some actual nodes here. So this means, okay, well, we have the start of the next list, and that's got to be added onto the end of this list. And we don't know how many nodes there are. We just know that, oh, we at least have one node after this. So we need to step through the actual and find the actual last node. So let's go back to our drawing and get a scenario drawn out so you can understand, visually see what I'm talking about. So let's assume that we have something like this. Head 1. Say 1, 2, 3 for data. We then have head 2 with some data here. Say A, B, right here. And so we know we need to move all of this tacked on to the end of what comes up here. So we need a reference to this node here at the actual end so that its next reference will be linked down to here. But we don't have a direct reference to that in the beginning. We can't just jump there with linked lists. We need to actually take a reference from the beginning and step it forwards. So if I pick another different color pen again, let's go with green, is what you need to do is, again, set a reference to the beginning, similar to what we were doing for printing. So we set it to the head, and we keep moving until it hits this node. So we've detected we're at the last node, not gone off the list, but we're at the actual last node. So it has to look, okay, is cur.getNext right here, is that null, that arrow? Well, it isn't. So then you move the current reference forwards. So draw that back so I didn't accidentally delete that. Move here. Is that next reference null? No, we'll move it to the next one. Cur right here. Is that next reference null? So yes, stop. Because now once we do that, once we have that, we can come back and now update this. So this reference equals the start of this other one. So cur.next is equal to start of this list. And then we can set the head 2 to null after that. And then you can see that we have the flow of the entire list being appended properly from there. So that the 1, 2, 3, 4, 5, and then we have the end of the actual list. So switching back to the code, this is where a helper method would be really good. Like getting this end of the node could happen and be used in other things that we're working on. And so also just break up the code. This is why I created this one here, get last node. So it gives you the start of a list and it will return back either null if the list is empty, or it will actually return back the actual last node in the list. So we set up our moving kind of pointer. Doesn't have to be called cur. I just like to use cur to be like represent current node that we're at. We attach it to the linked list so it's at the beginning. And then we want to move it again continuously through the list. And we want to stop when we've hit the end. And I apparently still can't type and talk at the same time. Okay, so the idea here is we go in the very beginning. If the list is empty, for right here, we'll have an issue here so far that I need to fix, is making sure that cur isn't actually null. Right here. So we have to worry about this. We have to make sure if the list is not null. I threw that in here because if I go cur equals head, then I cur arrow next, I'm trying to dereference a null pointer and that will crash it. So I'm worrying about the case, okay, if the list is empty, so I've attached to the list, if the list is empty, don't do anything, just end up returning back the actual reference. So again, if the list is empty, it won't go into this actual if, it'll come down here and return and end up returning back null. If it isn't empty, it'll go in and it'll check, okay, current reference, is the next node I'm looking at null? If it is, it means the current reference is at the last node of the list. So this could be if there's one node in the list or more. If it isn't null, then step in and move the actual reference forwards from right here. And so by the time we come out of this, it'll either be null because the list is empty, or cur will be the last node in the actual list. And so we need that here. So now down here, this means, okay, we need to get the last node from head 1. So node and specifically make sure that we are giving it head 1. So when we come out of that function, last node will be at the very end of this list, and we need to link that node to the start of this list. We don't need to copy anything else from right here because we just need to link. If I link this one node, that's completing that chain. So if we go back to the picture here, you can see that we have last node would be right here. So we would be, last node would be referencing right there. So I'm calling ln for last node. And then by going next, we're linking it down to here, and we have all the rest of these that keep chaining off to actually do this. So we should have this working for the actual append. So before going on to anything else, let's go and actually validate this. Let's go Control X, Control F. In our main, we know we've created the first lists here. So this list will be 1, 2, 3, 4, 5. This list will be 1, 2, 3, 4. We then have a call to append here being list 1 and list 2. So all of list 2 will be on the end of list 1. So I should see 1, 2, 3, 4, 5, 1, 2, 3, 4 right here. And then I should see that list 2 is set to null. So coming out of this, this list 1 will be longer. List 2, 3, and 4 will still be null on that. After that, we have a case of list 3 being appended on here. So list 3 is null from before. So we should just see that everything that was in 1 is now been moved into list 2, and then list 1 will be null. So this will be null, this will be null, this will list all the actual nodes, and then this last one will be null. So let's go back and see if I've got any compilation errors. No, and we are good so far. So we can go up and check the actual output. From right here, we see the original prints right here. We see after the actual append, so we see 1, 2, 3, 4, 5, 1, 2, 3, 4. So we are good with that first one, and we can see that list 2 is blank. Then we've got the second append where we're taking list 1 being added onto the end of list 2. So we can see good, list 1 is all blank, and now list 3 is 1, 2, 3, 4, 5, 1, 2, 3, 4. So we are good so far. So we've got this actual append. So the next part is for marks to hand in, you need to complete the reverse method. And so we can see that as this last call down here is that we're taking list 3 and reversing and putting it into list 4. And we should see list 3 will be the original list, and list 4 will be a reversed copy of list 3. So the reverse function, so this is you need to hand in for marks, and to get full marks you need to have also completed the actual append and the actual write list method that we just did together, so it has to be in the actual code, and then you must also complete the actual reverse method. So we need to design a reverse method, and this function must take a list as input and return a new list, which is the reverse of the original. So the original must not be affected or changed, and your solution must perform only one traversal of the input list. So it only goes over it once. So we have to step through our original list one by one, and as we step through each node, we need to construct the reversed list. So let's go back to list.cpp. Here. So remember, this is for marks, and I'm just going to guide you through the whole thing. So first step before we're doing anything, we need to make a new list and link everything into it. So I need to have a new head or reference to the start of that new list. So I will call this rev list, not rec list, rev list for a reverse list. And I'm just going to set it to null here in the beginning. And before I do any code, I'm just going to then actually return back that reference, and knowing that, okay, I will make an entire copy of it. The new reverse list will be here. Now, one case we need to deal with directly is always worrying about is what if this list we've been given is empty? So what could happen there? So that's one case we need to deal with is what if head is equal to null, so there is no nodes right here, or else what if it does have nodes? And we know if we're reversing the list, if this list is empty, the reverse list should be empty. So what we can actually do is not even worry about splitting up these two cases, is I can actually just change this into one of going head does not equal null. So if it isn't null, we will reverse the list. And so what happens here, remembering that if head is null, it won't go into this if, it'll come down here, it'll go to the return and return back null and do what the function is supposed to do. Otherwise, in here, we actually have to go through now and reverse the list. Now, we can worry about building the reverse list later. We can now go back to the tool I said at the beginning of the lab, is that general thing you need to do to actually step through the entire list. Just that. And we can get that working first, just to go through each node one by one, and then we can worry about building the reverse list. So to step through the list, we set up a reference to move through it. So we link into it, so your current reference equal to null. Current will be the one that we move forwards. We don't want to remove forwards the actual head reference. Even though that this is a copy to everything else, I still like to use a separate reference. So it's not passed by reference. So if we change the head pointer, what's going to want to change the original list, but I still prefer just to use this current reference to step through. We want to go through every node. So we go until it drops off the end of the singly linked list. And then we can do our work with our node right here. But before we leave here, we need to actually step it forwards, otherwise we'll have an infinite list. So moved, next node. So stepping that reference forwards. Okay, so that will step through it. Before I go on, I just want to make sure that this compiles. So we're good. It's still the same thing that we saw before. Our reverse is not doing anything here yet for the list. So next we need to step through this and keep building the list. And what we know is, like, let's go and try to do this a little bit in the actual drawing. Let's draw up a case and see what could happen. So I'll just move this up. And so what we assume is that we have a list here. And let's just draw it out, not even worry about the code, but what would happen if we were drawing it. So we have our head list, and I'm just going to go with 3 values. So let's assume we have a list with the numbers 1, 2, and 3 in it, and then it's ending with null right here. And so what's supposed to happen is that first I'll have this current reference right here. We have right here. And so we would have to go reverse, is that this is the start node. This needs to be the last node. So right here, so it has to be 1. And then as we move forwards here, 2 has to be the next node here that then links to 1. Curve has to be right here. And then the same thing here is that you have to have the 3. So 2, then 3. So as you move forwards, so as your current reference is moving here, something has to be moving back this way. And we have to always be keeping a reference to the start of that reversed actual list. So if we're doing any of this actual moving, what would be nice is, just like I have the current reference here, we should also have a reference that keeps moving backwards, but we have to define what does that moving backwards mean. And we always want to have that starting rev list. So what if we start from right here is that, okay, when we have current in the very beginning of 1, we know that has to be the end of the list. So if we have our reverse list, and in the very beginning before we loop, we just make it equal to 1 in the beginning. So assuming that that's the 1 node in here, and we're done and we have to go for current. Now what happens here that's different is that as current, let me redraw this a little bit better so it'll fit better on the screen. We have current here, and so before we go into the loop, we have a reverse list, and we make it a copy of that first node. So just like this, we get the data out, we make an actual copy. Next, when we can move forwards, we move the current reference, so it moves over to here. And now we want to make a new node, but what we can do is we can make a new node right here, temporary, and we can make a temp reference which holds on to that. So that's null. Copy the actual data, and the idea is that, copy that data, which is 2, is that we still have this reverse head list right here that's just holding that previous node. So we had this kind of like an add before, is that we can make our temp node next referenced over to what reverse list is currently doing, so right there. And then we can then move our list reference to be back here because we have this reference and this reference. So again, taking out my little arrows, is the steps for being this is that we have the current reference, we make a new node, copy the data, this is null. We then have our temp reference dot set next to be what is the reverse list. So that next reference over here, and then the reverse list we want to move back over here so that we're at the start of the list. So we make a reverse list equal to our temp list, the pointer, and we are right there. And you can see so far we have a reversal of where the lists were at. So then if we move again, current reference to the next one, we have a similar thing. We use our temp reference to hold a new node right here, which would have 3. We then sent temp reference dot set next is equal to the current head of the reverse list. So right there, the reverse list equals the temp. And we have a reverse of our list. So this takes a little bit of weirdness and practice, and I know my drawings quickly, but trying to keep this tutorial within 50 minutes for right now. But we can go back and we need references to move through and the importance of these actual pointers. So we know we have, first off, that reverse list. We know that if we're coming into here, the list isn't null, so there's at least one node. So the first thing we do before doing anything else is create that first node and copy the actual data over. So it's the head. So we will go head equals new node to dynamically allocate it right here. Ooh, and this is not head, sorry, that is rev list. So is that RL we saw before is the new node. We made the node, now we need to copy over the data. So I'm accessing the new node we have, and I'm copying the data from the actual current node. So copying that first node since it's head, making a new node, copying the actual data over. Now this next step you don't need to do. So next equals null. This is just something I like to do to guarantee that the node I have right now is not linked to anything. So by default the system should be putting the null there, but I just like to always make sure to guarantee that I've coded and told it to put null into that next reference. So that is setting up that very first node. So that's the same as with the drawing when we made this first node right here. So next we need to go through and move through the nodes and now keep linking everything together. So in this case now we're working with the nodes is that I've already added the new one, and then we're seeing, okay, we want to move the node to the next one to start with. So what I'm going to do right here is now that I've copied that first one, I am just going to go cur equals cur arrow next. I'm going to move it past this one so that the rest of it, so we've copied the very first node in the list, and then this loop will repeat the rest of the pattern. And this is just needed because when we're starting out the reverse list, we need to have a beginning reference that we're holding on to. And so cur will always keep moving forwards right here for stuff, and then this will always be the marking of the start of our current list. So if it's not null, we'll be going through some similar steps right here, but first what I'll do is I'm going to make a temporary node to copy what current is. So if it isn't null, I want to add it into the list. So I'm going node temp equals new node. So allocate a new node, copy the data from our current node, right there. And then next what we need to do is we're going our temp arrow next equals rev list, And so we know that, okay, we made a new list and there was the one node that's up here. We made a new node right here, and so now, well, this new node should be the new start of the list because we're reversing things. And so we're now updating first that, okay, my new start of the list links to my old start of the list, and then now moving the marker for what is the node that's the start of my list here. So I am not dereferencing the pointers in this case. So this is the case where now this is the rev list moving backwards from right here. And then we move on to the next one right here. So each time. So again, first one, copy the node over, set the start of your list. And then we're moving to the next node. Then this one here is going backwards, that we're making a new node for the data. We're saying it links to the old start of a reverse list, and then moving our reverse list back. So just like you saw in the previous drawings. So let's see if this compiles properly and if it runs. So far we're good. We can see down here for the list that we went through the last time for the append. We can see that we are doing a reverse on list 3 and it's being put into list 4. So you can see list 3 is 1, 2, 3, 4, 5, 1, 2, 3, 4. And we can see here we get 4, 3, 2, 1, 5, 4, 3, 2, 1. So it is. This is a perfectly reverse list. So there you guys go. So a little confusing, so you should take some time to actually draw this out and actually make sure you've got all of this code. I also will make this screen a little bit bigger here, so if you want to pause the video so you can copy this code out right now. So we are at the actual end, and I know I went through maybe this a little bit fast, whatever, it's 50 minutes. That's what I got for the tutorial for stuff, but you can see all these steps here, and this is good practice to make sure that you're getting through it. So you can pause the video here to start copying this code over and making sure that you're understanding it. So I would say pause. Here we have the append method if you didn't see that before, so you can pause again and see that code. Here you can see that get last node method that you should have. And then here is the write list. So when you guys hand this in, I expect to see the write list, the get last node, the append method, and the reverse here all working with that actual main and submitting the entire code to me. Otherwise, I hope you all continue to be great people and that you're doing the best you can at this time of year as we get closer to midterm season and everything else that's going on.